then, okay, we waited a minute and we can start officially. Okay, so good afternoon, everyone. Welcome to the first NITheP Colloquium of 2021. I hope everybody had a good time over the festive season and a good start in the new year. And if it is not too late, I wish you all the best for 2021. And we are working to organize a very nice series of colloquia for this year as well. This afternoon, we are very happy to start with an excellent speaker. We have Professor Sera Markoff from Amsterdam, who will give an exciting talk about putting the hair on black holes. Yeah, and I will ask Amanda Feldman, Professor Amanda Feldman from UCT, who knows Sera since a long time, to introduce her in a second. Yeah? Before I do so, I just wanted to alert the younger part of the audience, the students, that Professor Markoff kindly offered after her talk to spend half an hour just speaking to the students, and I just learned from Ying-She Ma that Sera Markoff gives excellent talks on career advice for students. So some of you might want to stay on after the talk, and she will be very happy to interact with you and answer your questions. And I will be very happy to transform the webinar into a meeting so that everybody can speak and interact with Sera. And with us on the panel is also Professor Ying-She Ma, who kindly agreed to moderate the question and answer session after and during the talk. And please make use of the Q&A facility or raise the hand with the buttons at the bottom of your screen. And Professor, and we have to congratulate Ilya, because between the last talk and now he became professor. So Ilya, congratulations to that. Is as usual happy to be the backup plan and co-host the event in case my internet connection fails or something else happens. Okay, so now it's time to start. So Amanda, can I kindly ask you to introduce the speaker?
With pleasure. So today we're extremely lucky to have Professor Markoff joining us for this NITheP Colloquium. For those of you who don't know her research is in what is arguably the most exciting nexus of ideas happening in gravity, astroparticle physics, and astrophysics. And we're going to get a very exciting talk today. I'm especially looking forward to it. I think my summary of her title is the difference between astrophysics, the real astrophysical black holes, and theory black holes. So putting the hair on black holes, which is a very exciting topic. Sera's had an extremely interesting and illustrious career so far. She completed her PhD at the University of Arizona and won a very prestigious Humboldt Research Fellowship to go to the Max Planck Institute for Radio Astronomy in Germany, and then went back to the US. You can see she's bounced between continents, back to the US, where she was a postdoc at MIT, and finally back to Europe, where she began as faculty at the University of Amsterdam and has risen, I think, pretty quickly to the top. She's a full professor there now and helped to launch the extremely popular and successful grappa, not the drink, which South Africans right now would be grateful to be offered, but the Gravitation and Astroparticle Physics Amsterdam Center of Excellence. She's won a number of research awards, and I think is probably so modest that she'll be uncomfortable if I list all of them, but they include a fellowship from the American Physical Society, a number of outreach awards for her remarkable EDI work, including one from the Dutch Research Council. And of course, she's a member of the very exciting Event Horizon Telescope collaboration. So she bridges that phenomenal divide between theory and data, and I think we're going to get a very exciting talk. So I hope you all will enjoy. And just to reiterate what we've just heard, after 1 hour, everybody who already has a PhD is going to leave the session so that the session is only available for students, master's students, undergraduate students, postgrad students, doctoral students.
PhD students definitely are welcome.
Yeah, it's aimed at PhD students. If you have a PhD, when we're done with questions and answers, then we will all leave, and it'll just be students. And I'm sure that they'll be given the option of whether or not they want that section of the talk recorded. So without further ado, on to Professor Markoff.
All right, well, thanks so much for all the introduction. You've kind of stolen my punchlines, actually. Let me try to share my screen while I get this going. Okay. And I hope this looks, whoops, good to, hold on one second. It just sort of got rid of the wrong thing on my screen. Everything always works fine until you share. Let me try that again because it just sort of vanished on my screen. Okay. Okay, is that visible to everybody? I'm going to assume. Yes. Okay, yeah. Good. Sorry. Yeah, somehow it went off the screen when I hit share, but now it's working. All right. Well, thanks everybody for coming in today. And I'm sorry I can't be here in person. I would love to be able to visit South Africa again. It's been quite a while since I was there, and I've only been there twice. So I think many of you are sitting in cities that I've never been to. Anyway, so as Amanda said, I want to talk to you about, well, this idea of what it means to put hair on black holes. And kind of jokingly, what I mean by that, of course, is exactly what she said, which is that when you see a black hole in its more, realistic natural environments in outer space someplace, it's usually surrounded by a bunch of material. If it isn't, then we can't see it. So we pick the ones out that have what we call accretion, or it's capturing matter basically via its gravitational pull, and it's launching a bunch of interesting physics around it. And so two black holes that would normally, according to general relativity, have the same basic properties like mass and spin and be indistinguishable will actually end up being very distinguishable because of all the stuff that's around them, the hair, which is the astrophysics for us. Now I'm an astrophysicist, so that's the part I'm the most interested in, but I'll try to give you a good sense of how this connects also to the questions that some of you might have more about fundamental physics and GR. From the astrophysics side, we're really interested in, for instance, these things that black holes basically expel from near their event horizons. In particular, I'll be focusing on these things called jets. These are basically magnetized plasma jets that are moving relativistically. And we have a lot of questions about how they're launched, what's inside them, are they able to tap the energy of black holes? And also even what happens in terms of dissipation to actually allow particles to get accelerated to make the light that we see. And since EHT has now given us the first direct view of sort of these regions just around the event horizon of one black hole so far, and we're working on one other one, it's become a question of how do we connect this little donut that we saw to all of these other structures on much larger scales, and the inversion about how do we use all these things that we see to actually try to pick out the part about GR. So I'll get to that over the talk. So I just want to mention again, as Amanda said, I'm speaking kind of with two hats on. I'm a member of the EHT collaboration. I'm currently the vice chair of the Science Council, and I'm co-running this working group on multi-wavelength observations. I'll explain what that means later. But I also have my research group. And so when I talk about EHT, I'm representing hundreds of people and a lot of work of young people, but also in my group. In orange, I highlight former and current students and postdocs who've led the research usually. So you'll always see their names in orange. And then I have some external collaborators I've been working with on some things I'll say. Okay, so before I get into the real details of the talk, I know that a lot of you are coming from very broad backgrounds, many from physics, maybe computational science. So I want to give you a sense of why we study black holes from the astrophysics side. And an image says 1,000 words. So I think the best is I'll show you some pictures. But basically what you're looking at here is an image taken by the famous Hubble telescope in space. So it's an optical image. This is what your eyes would see if they were really good and you could see far out in space. And this is what's called a cluster of galaxies. So all of these dots are not stars, they are galaxies. And it's the largest bound structure of matter in the universe. And we sort of think of these as the nurseries of galaxies. These are where galaxies form and interact and grow. And in the very center of the cluster, where gravity pulls things to the center, you have the largest galaxy. And you see this very bright. A lot of this is from stars, but there's also quite a lot of light coming from a black hole, which has been accreting, which is pulling matter towards it, and it lights up. And this accretion process occurs on many different kinds of scales. I'll show you some pictures of that as well, but things that are multi-scale tend to basically translate into multi-frequency, multi-wavelength in terms of light, because light is sourced at a certain scale, and that gives you information about the frequency that sort of determines the frequency that it comes out. And so if you want to understand these systems, you have to look at them in basically as many wavelengths as you can. They radiate from radio all the way up to gamma rays, so the entire electromagnetic spectrum. So if we switch now to look at another wavelength, so optical is what your eyes see. Now we're going to move to things that your eyes can't see, but we translate the colors fakely, so the color means nothing really, to see what the radio telescope would look like. And radio, basically the emission that we're looking at is non-thermal, so it's out of equilibrium. It comes from synchrotron emission, which means you have basically relativistic particles that are moving in a magnetic field. So it's tracing energetic relativistic plasma with strong magnetic fields. Same exact image, but now in the radio. And you see something dramatically different. These are those jets I was talking about. The black hole is able to launch these things. They're crazy huge. These are about 800,000 light years across, or if you like kilometers, that helps. I think it's just useful to remember this is about 1 billion times bigger than the black hole event horizon that launches them. And they carry an enormous amount of energy that really has a huge impact on their environment. So what we can do is we can calculate how much energy is here by looking at how these jets have basically pushed through surrounding medium and pushed open the space that they occupy. So to do that, we can look at another wavelength, which is X-ray, again, fake color. And now you see in the X-ray, what's happening is this is gas, hot gas that's been heated and trapped between all of these different galaxies. There's a lot of structure. This is that central galaxy again. There's some bubbles. This maybe came from winds that were coming out of the side. The jets we saw are coming along this way. And if I put it all together, so this million-degree high pressure gas had to be pushed out of the way. You can't see it so well, but in some images too, you can see really the bubbles. We can calculate the PDV work basically just to see how much energy was pushed out, put in here to push that away. And we find that it's about something like 100 billion supernova of energy can be deposited during an active phase of one black hole, a big black hole in this case. But that gives you a sense of the amount of energy it can affect. Basically, its host galaxy, galaxies surrounding it. It dumps a lot of heat. Heat gives pressure to the gas, and it keeps it from condensing and cooling. And that's what you need to have happen to get star formation to make galaxies grow. So we think there's been this interplay between black holes and their host galaxies, their host clusters, since very early in the universe. And we need to account for this in our models of cosmology. But we don't actually have an a priori first principle kind of model for this. And that's something from the astrophysics side we'd really like to do. So if we want to understand this, we have to zoom in on where all this energy is sourced, which is near the event horizon. Oh yeah, and I forgot to mention, for those of you interested in particles, these jets, of course, are also thought to be the big sort of large hadron colliders of CERN in outer space, and they can accelerate particles to millions of times more than you could do on Earth. So they're also a place where you can probe a lot of cool physics of the collision scale and QCD and so on. So this is an artist's impression because we don't really have a perfect image of these regions close to the black hole. With EHT, we're seeing something, but the question is what? And what's really going on, what we think, is that you have multiple phases in this accretion disk. You have something like a condensed corona, like the corona of the sun, very diffuse and magnetized. There's these jets, there's winds. All of these different phases emit light in different processes. There's turbulence and instabilities. And so it's pretty complicated. And one of the big questions that we're sort of plagued with is how do we go from these big macroscopic things that we see to the microscopic processes that actually make the light and put it all together? It's an interpretation problem. And one of reasons that it's very difficult to model this from first principles all at once is just because of this dynamic range and scales. And so, for instance, many groups are working, and I'll mention this a bit later, on kinetic simulations, where they actually will take, background magnetic fields and densities and really try to mock up from first principles how particles will be energized in a plasma like this. But the problem is that to do this, they're so computationally expensive that you look at the box size, and these are expressed in terms of basically plasma, ion wavelengths, plasma wavelengths. So they're really teeny tiny compared to these enormous systems. As I said, they can be billions of times bigger than the event horizon. And so we can't put this all into one computer simulation and run everything. It's just not possible at the moment. So what we do is we break the problem into different pieces and we try to put it together. But that, of course, introduces uncertainties, errors, and so on. And I'll try to give you a sense of how that actually translates into the Event Horizon Telescope and other interpretation for us. So the outline of my talk is I'll start off, I'm not going to go into great detail about the 2017 results because I assume by now you've probably heard some talks about this, but I'll say that in the context of this question about the interpretation of the astrophysics, a little bit about the GR, I'll focus mostly on what we're trying to do to improve these astrophysical uncertainties, and I'll, towards the end of my talk, give a real concrete example of some new work that's really like state of the art and not published yet, but just what we're working on at the moment. And then some outlook at the end about where things are going to be going in the coming years. Okay, so this is the famous, I call it the fiery donut. Again, the colors are fake. Just remember that it could as well have been green or pink or something, but somehow this is a very common color scheme. We picked this and it turned out to be the right color scheme because people really liked it. And this is a Zoom snapshot from our last collaboration meeting online. So you get a sense that there's hundreds of people involved in this collaboration. Now, the papers, there were 6 papers presented from the 2017 campaign. About 2 years later, we published, and it gives you all the information about, the data taking, the analysis, everything I'm going to talk about. You can read the details. There's also a companion paper about the codes that I'll be saying a little bit more about. And one of my PhD students was very involved in that. But what you have to remember is that this is a reconstructed image. So it's not like an optical telescope or a camera where you have a lens and you basically just put something on a pixel exactly as your eyes would see. Interferometers, and this is in this case a millimeter wave, but it's like radio wave, just a little higher frequency, are basically sampling the pattern of light on the sky as a function of size on the sky, which translates into the baseline between dishes in an array on the ground. So it's basically a Fourier spectrum of the light pattern. So you're probably, maybe some of you are familiar with this, with the cosmic microwave background, that people break up the pattern on the sky into this, Bessel functions. That's more or less what this is a Bessel function. And the baselines here are expressed in giga wavelengths. But you see that the largest baselines are basically limited by the size of the Earth, and that translates into the smallest scales we can see, and it's sparsely sampled. And so when we invert this and reconstruct to the image, that introduces the resolution effects, effectively give us this blurriness to it. So we're basically seeing directly the effects of gravity, but in 2 different ways. There's the focusing of light around the event horizon, which is the part that might give promise to really directly looking at the space-time shape and the GR testing. But then there's the gravitational energy release that the astrophysics that's surrounding this are also dependent on. And we have to try to pick these different pieces apart. So there's been some really nice work. Recently, there's a great paper by my colleague, Michael Johnson. These visualizations I'm showing you from him and George Wong. There's also some nice papers going back a ways. But we can start to understand this image by breaking it into effectively orders of half photon orbits. It's really confusing because different papers use different, I think Gralla et al. Use full orbits, there's plane crossings. I like the half orbit breakdown because what you could do is say, okay, every photon that we're going to trace per order, the number tells you whether it completed a half orbit around the black hole. So n equals 0 means that either the photons are coming directly to you or they got mildly bent by, or mildly lensed by the black hole. And then of course, that means that most of the photons that you see at infinity in this direction are coming either from behind you or they can come in front, which isn't shown in this movie, but as long as they don't block the light from around the black hole, you'll still see the shadow. And so this movie shows the n=0 order first. And what you're seeing is that, light is coming in this visualization mostly from behind. It's being slightly distorted, and whatever path hits the black hole gets absorbed. And that image that we just saw, this n=0, is basically where most of the astrophysics is, or it's very strongly dependent on the astrophysics because it's directly coming to you. It's going to reflect the geometry, the plasmic properties. It will have Doppler shifting due to the motions and so on. But if we go to the n=1 order, then these are photons that make a half to a full orbit, which means that they're going to be strongly lensed by the black hole. They can be coming in from all different directions, basically from the astrophysical plasma that created the light, but they're going to get strongly lensed into this tight ring. And well, actually, I won't stop it here. I'll just keep going. But anyway, so this ring is pretty bright. I'll show you in a second. And then you can keep going up higher and higher orders that will bring you closer and closer to this critical orbit that's the last, basically unstable orbit that photons can go many times around the black hole before eventually escaping to you. When we look at the entire image, then we're seeing all of this convolve together. And of course, we don't have the perfect telescope. So we would expect that this bright ring, the n=1 ring, is kind of the dominant feature. Basically, if we took a slice through this, so this is distance from the black hole, you can see the n=0 or the underlying astrophysics. Then you've got this brighter but relatively wide ring, and each successive order will get narrower and narrower and brighter, but actually become indistinguishable on the image. And so depending on the astrophysics, the orientation, the spin, and so on, it's somewhere on the orders of 10% of the flux. And the idea is that if you can pick it out, then this shape will trace the shape of space-time and will tell you, in the case of GR, basically the mass of the black hole, or you can use it to test GR if there's a deviation. And there's a lot of predictions about what this should actually look like. So the tools that we use to interpret our results from the theoretical side in the EHT collaboration are general relativistic magnetohydrodynamic simulations, or GRMHD. And this is one example. This is actually a movie made for another black hole, the second target, Sagittarius A star, which is smaller and more variable. So over time, you see a lot more variation. And that's part of what I wanted to show you, is that this is a simulation of what you would see with a perfect camera. You see that the photon ring is a pretty robust feature. So again, if you could get multiple snapshots, variability would play in your favor because you could average the images and you would be able to maybe pick this feature out better. We can't do that yet, but that's one of the things we're planning to do in the coming years. So far, we just have these single snapshots, basically, of a very slow, big black hole, M87. But we know the size that GR predicts. This is work that goes back to the 70s and 80s, and it should be somewhere on the order, if you talk about the gravitational radius, which is gm/c² or m/d in natural units, this angular radius on the size, because I put the d there, that's the distance to the black hole. So it's going to be 10 times this m/d roughly for Schwarzschild, with about a 4% error. It can be bigger or smaller for Kerr black holes, depending on the spin and the orientation, but it's not super sensitive to this. And it's usually going to be pretty circular. At the most extreme cases, you can end up seeing a little bit of a deviation to be a bit of a D shape, but it still has generally this size and shape. The problem is, of course, when we have our reconstructed non-perfect telescope, this is what we see, right? It's something fuzzy like this. And the question is, can we draw a ring through this and associate it with this photon ring, or will there be an offset because of the astrophysics? And that's been where a lot of the work is focusing on, is trying to figure out this bias. So this angular diameter, again, you could break it into the GR part, this prefactor times gm/c²d. And then you can say there's maybe this bias or shift factor that corrects for the astrophysics. That's what we need to figure out our uncertainties in, to figure out how well we can, for instance, test a deviation from GR. And so we can express the deviation from GR in terms of this delta parameter here. And so if you look in the papers, and I won't go into great detail, you can see all the analysis, but this is basically the probability, the posterior probability distributions of the angular size. And so here's your GR prediction with the 4% error. And these are the probability functions from our analysis, basically from our astrophysical fits. And you can see that, we have some observational systematic uncertainties. These are pretty small, but this big red thing here is basically the theoretical uncertainty. So this is telling us that we really have a 10% error in terms of knowing which theoretical underlying models within this suite of simulations that we made, and I'll say more about that later, really explain this, the ring size. And so this number, this 4 factor, has been estimated to be 11.5, so it's a bit off of 10, it's bigger, so astrophysics tends to bias the ring a little bit bigger. And then we have information about the mass and the distance. These are our priors from astronomical measurements. And basically we could then do a probability analysis to say, what's the probability that we're actually deviating from the predictions of Kerr? And the Kerr metric, is here for, in this case, the stellar dynamical mass. So this means the mass of the black hole that have been measured from the motions of stars versus the mass of the black hole based on gas dynamics. And they were about a factor of 2. So before we did this, we didn't actually know which of these was correct, but our results land basically here and say that if Kerr is correct, we're sitting pretty close to no deviation on the stellar dynamical mass, but at the 68th percentile, we have about a 17% error. So that's as good as we can get at the moment in terms of testing GR. And it doesn't sound that great. I mean, I have to say, when I first heard this number, I thought, okay, obviously gravitational waves and other things are going to be much stronger tests, but, and I'm not the expert on this, so I don't want to say too much about it, but I'm going to point you to the work of my colleague, Dimitris Psaltis, also part of EHT, who's really been leading this work for many, many years. And most recently, he's been looking at, for instance, these parametric post-Newtonian expansions to compare the results with, for instance, solar system tests and gravitational wave tests of GR. And surprisingly, in these sort of treatments, you can really narrow it down to particular terms in this expansion, and you find out that the M87 shadow measurement actually can be 500 times better compared to these weak field tests in the solar system, and roughly on the same order. This is EHT again compared to the 2 gravitational wave sources here as LIGO Virgo results. So we're not doing so bad, but what we'd like to do is, of course, do better and to really be able to narrow down this understanding of the bias and in different ways, basically reduce this fractional spread, this deviation, so that we can really start to test the physics. At least, this is the interest from the theoretical physics side. And one way we can do this is we can make a better telescope. So we can add more telescopes to the array. We can go to outer space. I'll come back to this. But actually, since the errors were really dominated right now by the theoretical uncertainties in this gas around the black hole, we're concentrating, and there's a huge amount of work actually improving this at the moment. And that's where I'm going to be focusing on this talk mostly. So now I'm moving into this idea of how do we actually go about reducing these uncertainties, and what are the uncertainties? So if you look in the collaboration, there's more or less a few main directions in how we're going about this. One of the things that we can do is we can compare predictions of the stuff that we think should be coming out of black holes, like these big plasma jets, to direct images, because we actually see these things all the time, and also to power estimates from observations. So we have theory, either semi-analytical theory or from these GR MHD simulations, and we actually have some observational tests. So I'll talk about that first. The next thing would be that we don't really get into the details of the microphysics of how light is produced, because this is one of our biggest uncertainties, but we make simple approximations, and then either semi-analytically or with GR-MHD, we can make full spectra, and we can compare not just the EHT images, but also to these multi-wavelength observations, kind of like I showed you, from radio to X-ray and even gamma ray. And that can really reduce our parameter space. And then if we really want to start getting into the nitty-gritty, we can go down to trying to understand more these non-ideal dissipative processes that lead to particle acceleration in the microphysics. And again, try to compare to multi-wavelength observations. Now, this is something I often call like benchmarking observations to simulations. And I'll give a very specific view of this at the end. We'll see how time goes. So the first thing I want to mention is this idea of comparing basically these the shape to images, because here's a schematic again of a slice of the system. So you have this, I mean, it's totally not to scale. Don't get hung up on that. There's like a donut torus of material, and this is a jet. And to first order, we can think of jets as just a conserved flow of magnetized fluid. So it gets into the fluid dynamics, and we could do a lot of stuff semi-analytically. We often use this parameter sigma, which represents the magnetization. So it's just the ratio of the magnetic energy to the total energy flux in this flow. And we think more or less that it's the magnetic energy that's doing a lot of the work here. So you start off with some stronger magnetic fields, and basically pressure gradient forces and hoop squeezing and so on from the fields can push the plasma along. And then this gamma is the Lorentz factor. So it's how fast the jet's moving. So it's basically accelerating, and you're losing magnetic energy. So this gives you also a profile of magnetic energy decreasing along the jets. This has been worked out in a lot of ways semi-analytically, especially for ideal cold plasma. So you're not worrying about dissipation, you're not worrying about how you heat the particles, and you're just pushing, protons along, which is most of the dynamics. And if we treat this as a conserved quantity, this the specific energy total, which is basically the total power divided by the mass power, m dot is the accretion rate or the amount of mass in the jets or in the disk actually coming in, sort of your original energy budget. What you see is it's basically a perfect conversion process in this ideal case. And so you start as you move along the jets, this mu is conserved and magnetic energy goes down and the jet gets accelerated. When you start adding dissipation, of course, you put energy into particles, and that will, for instance, some of this magnetic energy and turbulent energy will go into the particles. So you lose part of that. Actually, let me start. So this is an example. Ooh, sorry, that was not what I wanted to do. Yeah, okay, sorry. So this simulation is one, basically just to give you an idea of how we start, where we wrap a torus of material around a black hole in general relativistic metric. We can put any metric you like, so we can also test, exotic things. We see it with the magnetic field, and we can generally then basically launch jets, is what you're seeing, first principles. And in fact, now we're working with codes that are GPU accelerated, so we can really run these quite long and fast, and we can get to scales. Now, this is in units of these sort of the black hole radius, the gravitational radius. And we can go out to 10 to the 5, 10 to the 6 gravitational radii, which is basically the scales that we can also observe. And the shape of the jet will tell you something about the pressure balance. So you get a lot of information just by measuring, for instance, the opening angle and the distribution of velocities. And this is an example of our target M87. This is with a slightly longer wavelength. So we're looking at larger scales. The EHT image would be buried down in here in this bright spot, but these are the jets. In the opening angle of the jet, we can measure this. We see that the jets are sort of lit up more on the side. That's something I'll come back to, but we can draw a line through here. So here's the radius as a function of distance. And you can see this red line is from our simulations going out to very large scales. And this is data. And these are also the Lorentz factors, a little bit more messy in the simulations, but we're sort of on the right track. It looks like, at least when it comes to this bulk dynamical motion, we have a pretty good understanding of how the jets are formed, what it takes to push them along. But there's a lot at the detailed level, and there's quite a few variants within here that we need to be able to discern between. So some of the exciting things that we could do is start to use information from other frequencies, and that's what we call multi-wavelength. And for instance, use power estimates as another way to start to discern between these different models. And this is a movie, you could see these field lines now, that the magnetic fields come in through the disk and get squeezed in and help launch the jets. But there's theories going back to the 70s by Blanford and Znayak that when these colloidal field lines will thread the ergosphere of the black hole, which is this region predicted in general relativity for a parametric, that's basically going to be rotating with the black hole. It's the space-time itself is being effectively dragged. The magnetic fields can still escape. It's not the event horizon, it's just outside the event horizon. But what happens is the magnetic fields will get twisted up because of the action of space-time and can effectively tap the rotational energy of the black holes. And so this process has a particular prediction. It's been calculated semi-analytically. Now we see it in our computer simulations, but basically the power predicted in the jets will have this term that depends on the spin of space-time, the frame dragging by the black hole, as well as the magnetic flux threading the ergosphere and the total amount of matter, sort of your energy budget for the black hole from accretion. So one of the things you can do, for instance, is if you can measure these things, and that's something that we can do for these black holes, we can start to put limits on the accretion rate, on the amount of magnetic flux, and I'll show you next, we can measure the power total coming out of the black hole. We can start to either understand if the black hole is spinning and maybe make some constraints on that spin, or in general, if we can say 100% sure that the power coming out of these jets is actually more than it's taking in mass energy, then that jet has to be tapping the black hole's energy. And it's another way to prove a prediction of general relativity in terms of the parametric and frame dragging. So that's another exciting way to think about this, where the astrophysics taps into the theoretical physics questions in a different way than just the photon ring. So to give you an idea of how we do this, I showed you the jets inflate these bubbles. When we have measurements like that, we find that the inferred power can be quite a lot more than the amount of luminosity, the power coming out in light in these jets. It could be hundreds to 10 to the 4 times bigger. But we have this problem of causality because the bubbles are so far away from the core. Remember I said there were billions of distances away, but this translates into maybe tens of thousands, hundreds of thousands of years. You might be measuring a kind of integrated power and not actually the power that's coming out at the event horizon scales. And so that's not always the best estimate. If we can measure the power coming out from the lights in the inner jets, we call that the bolometric luminosity, then a conservative lower bound is just to say, okay, the jet can't be less powerful than the light that we're already measuring. So if we add up all the light, which we can do in nearby black holes like M87, and we measure it to be in this unit 10 to the 42 ergs per second, then that's a very conservative lower bound. And then what we do is we run our simulations, and this is what we did in paper 5, and we make projection tables. So we ran on the order of about 45 unique GRMHD high resolution simulations. These parameters here tell you about different choices in the astrophysics. I won't go into a lot of detail, but sane and mad have to do with weak magnetic fields, strong magnetic fields. You have the spin, retrograde to prograde. We have this parameter R high, which I will come to, which talks about how you light up the simulations, how the particles are being lit up in a simple way. And then, for instance, here you have the X-ray luminosity and the power in the jets. And we basically said any of our simulations that don't launch a jet that are powerful enough to beat this constraint fail. And it turns out that actually a lot of our models which pass the other criteria end up failing the power test. And so the multi-wavelength information we have about the power actually already helped us to reduce this parameter space, but we didn't fully incorporate that into our error analysis. So that's something that we're working on now, is how to really factor this in. Plus we're running more models. And the other thing to point out is that many of the simulations fail, but all the simulations with spin equals 0 fail. Doesn't matter if it's mad, strong magnetic field, or weak magnetic field. And so basically we can't say that we're proving this extraction of energy from the black hole, but it seems like it's a kind of difficult at the moment. Okay, we also have X-ray light. And we measure this for the source. And so we didn't fully exploit that for these early papers. We basically used it as a criteria of did our simulation with the most simple conservative way of adding light actually end up violating any of these constraints. And the next step is that we have to start doing a better job with this. So I'm going to move on to the next part of my talk, which is really about how we start getting down to these particle levels. And as I mentioned, if you want to do this right, you really have to go to these kinetic simulations where you take a background electromagnetic field and you let first principle physics happen, calculate Maxwell's equations iteratively with turbulence, and you start to build up your distributions. And we're really interested not just in this Maxwellian, which is how things start, but when they break from being thermal and get accelerated into a power law. How this relates back to what I said about the dynamics is that it seems that in most of these scenarios, the power law slope, which is what we can measure also from the light, actually depends on the magnetization. So we can start to break degeneracies by putting all of these things together. And so when we fit a particular image from the event horizon, we use some particular way of lighting up the simulation, we also inevitably will predict the light that comes out from this is flux as a function of frequency, and it's kind of the fingerprint of the black hole from radio up to X-ray. Now, just to give you a sense again about this degeneracy, I've said this before and I showed the movie, but this is basically a simulation where you're just looking at one instance of a simulation. Orange is the disk, jets are blue. We're looking at it about 17 degrees, 20 degrees down the axis of the jets, and you see a volume rendering. So you're seeing the outside of the disk and you're seeing kind of the outside of these jets. And what we're going to do is basically paint this simulation with some approximation about how the light is made, because these simulations are ideal. They only have protons, and protons aren't making most of the light. Most of the light are coming from high energy relativistic leptons. So we think that the protons heat these leptons via Coulomb exchange, and we make simple approximations. And one of the simplest things we could do is assume everything stays thermal, everything stays Maxwellian, but there's some prescription for how energy gets translated. And I won't go into the details of this, but basically this is work from, the reference was on a slide that I cut, I just realized, but by Monika Moskobrodska in 2016. This was one of her prescriptions. We have many different ones that we use, but same underlying simulation. And what we do is we change the single parameter, and this parameter controls the exchange of energy between the protons in the simulation, which are calculated self-consistently, to the electrons, which are basically added on post factum. And this parameter, if it's low, is lighting up electrons far from the black hole in the sort of least magnetized regions. And then if you turn this up higher, you light up preferentially particles that are in the very magnetized regions. So same exact underlying simulation, but you see that you start to get more distributed, kind of broad emission here, and it could be compact and have a very different morphology. And then when you blur it out, EHT would see something very different. And so, of course, what we try to do is explore all the parameter space where these types of things give us something that looks like EHT, but we still have a big parameter space to work through. And that's where these numbers end up having a big impact on the multi-wavelength observations as well. And so at the same time that we looked, here's the beautiful M87 galaxy, here's the jet, and we see these jets in multiple frequencies. So when we were looking with the EHT, we basically coordinated a huge multi-wavelength campaign. And this is showing you as a function of day. These were the EHT dates where we had our observations of M87. And these are telescopes from the radio all the way up to the gamma ray. And you can see that we have quite a lot of simultaneous and even a couple days later before information. Now we're working on the paper right now. This is basically the combined spectrum. So this is this unique fingerprint of light from radio all the way up to the gamma rays, TeV gamma rays from M87, quasi-simultaneous. So it's a really spectacular data set. And this one data point here is from EHT. So once you do the imaging, you still have all of this to explain. You have to be able to fit the image, but you also need to be able to explain all of this when you make these prescriptions. And that's the way that we're starting to move forward. So you stay tuned, because I think there's quite a lot coming. And I'm going to, so I guess we started with the introductions a little bit late, so I'm hoping I have a few more minutes because my clock is telling me it's 1:45 already, but I'll try to go through this a little quicker. I'll give you an example of really the state of the art of how we're trying to go further than these simple prescriptions and really try to understand how the dynamics link to the particle level processes. And then this would eventually be something we could turn around to get to the better test of GR. So this is a schematic again of a disk with a jet, and I've put it in this particular direction because when we go to the spectral energy distribution, the amount of light coming out as a function of frequency, it kind of maps on a frequency in a particular way that the regions nearest the black hole are the highest frequency or higher energy. So you get a kind of bump from this accretion disk. We expect to get a bump from this region, which is thermalized near the black hole, this corona and the base of the jets. And then somewhere along the jets, something happens, you get dissipation, and this power law that we actually detect starts to pop out. And the question is, where does this dissipation happen and what kicks it off? And in M87, here's again, I've shown you this plot, but this is the spectrum of M87 from a non-simultaneous older data set that we were looking at. But basically you could see here's the first bump from the accretion disk. Here's the thermalized bump from thermal particles near the black hole. And then this is basically, you could think of this as slices being added up along the jet from the black hole out to the very edge of the jets. And this power law, which is accounting for, this is galaxy light, so you don't want to account for this, but like for the X-rays, and it continues into the gamma rays, will connect back to this piece of the jet, and it's offset from the black hole. We see this in many, many black holes, that basically this power law component, this excitation, seems to happen some distance from the black hole, and that's a really big clue for us about what's happening in the plasma physics. We can fit for this with models, semi-analytical models, and in this case, it's about 100 gravitational radii, 100 black hole radii away from the black hole. But what's interesting is in actual maps, this is again the same black hole we looked at with EHT, but now an image made with a different frequency where we can't see the black hole itself, but we can see sort of on scales of tens of these gravitational radii at about the same distance that we seem to need particle acceleration. We start to see features like maybe there's a squeezing, and this could be some kind of collimation shock. It could be some King instability, maybe something macroscopic is happening to translate the energy into the particles. And so these are the kinds of things that we start to look at in our simulations. We're also very focused on regions along the edge where the jet interacts with this wind or accretion disk, that you could start to see two-stream instabilities, Kelvin-Helmholtz instabilities. And in these vortices, you can form, for instance, plasmoids, which are regions where magnetic field reconnection can happen, and that energy will be translated into particles. And actually, we think this is one of the primary ways that high energy particles are going to be excited. And you see that we focus on the edge of the jets because you basically see that the jets are actually edge brightened in the actual images. But the problem is that even though this is one of the highest resolution simulations that's been run, we're not actually resolving these plasmoids, but that's changing now. And I just want to highlight, this is brand new work that's being led by my two former students and Bart Riepeda, who's a postdoc in collaboration with several others. But we're running the largest ever 3D GRMHD simulation in terms of resolution. And basically, it's the first time that we're managing to get very thin current sheets at these levels that are very close to the black hole, which actually show plasmoids forming. And this color scale is in the ratio of gas energy to magnetic energy. So what you expect when you see reconnection is that you would have these little red spots surrounded by blue-green spots, basically telling you that magnetic energy has been dissipated into particles, and then surrounded by still intact magnetic fields with different orientations. So there's obviously a lot of work to be done, but this is exactly the kind of underlying physics that we need to, we can even start to combine this now with these kinds of kinetic simulations to get a more self-consistent idea of the particle acceleration. And this is a map showing you the temperature. And you could see in these ideal simulations, what happens is you're simply heating the thermal energy of the particles. But if we do the prescriptions better, we can start to understand the non-thermal, understand why we're heating up the sides of the jets and so on. So we're trying to benchmark information we have about observations to these actual very detailed simulations at the moment. Anyway, so I'm almost done. I just want to say a few things about the outlook and what's coming. I guess you all heard about the Nobel Prize. This went to, well, Roger Penrose for GR predictions, but Reinhard Genzel and Andrea Ghez did the work that means that this black hole is the best known in terms of the priors on the mass and the distance. This means that when we fit the images that we'll be getting from EHT, we'll have much better constraints as well also, and to reduce this fractional deviation from GR, for instance. It's a very, very well-studied black hole. And I'll just give you one more taste of kind of where this macrophysics comes in. The black hole is basically flickering. These are light curves, which means these show you, basically each of these boxes shows you a day in the X-ray looking at this black hole. And on average, every day it hiccups in the X-ray. Sometimes you see little hiccups, sometimes big hiccups. And these are, we think, magnetic reconnection events where, like this, kind of like the solar flares, particles are being, you get reconnection and particles get accelerated. And we did a multi-wavelength campaign during the EHT run as well. For 2017, we're analyzing all this at the moment. I'll skip over the light curves just to say that we see also blobs of emission in the infrared moving around the black hole with interferometry. So this is very exciting. And what we could do now with our very high resolution simulations where we start to form these plasmoids, each of these colors represents, you know, 2 weak field models, 2 strong field models, and we can make fake light curves. So basically fake data from the light that is produced in the simulations from EHT, millimeter band, in the infrared and the X-ray, and we can perform power spectra analysis and spectra and do all the work to try to basically compare, for instance, cumulative distribution functions. This is one way to characterize the variability in the infrared. Here are the colored lines are all the models, and the black line is what you get from very high quality data that we don't have for M87, but we have for Sagittarius Star. And we're not there yet, but the idea is that we can use this precise data to start bringing us closer to understanding how the light is produced, and that will really help us reduce the model space. The next thing coming up is polarization. Again, kind of saying the same point over and over again, we can have the same exact image, but the models can be very different with different spin, different magnetic field strength. However, if you look in the polarized light, there's a real break. You can really distinguish between these. And these papers are being worked on right now. We have polarization information for all the sources, and that's going to be a major, major breakthrough for us in this parameter space. We could do fun stuff like here you have a black hole which is rotating along this axis, but the disk that's feeding it is tilted with respect to it, and you get a kind of weird tug of war between this frame dragging around the black hole and the torques from gas pressure magnetic fields that want to keep the disk and the jet kind of sticking together. And we're actually looking at the consequences of this because more often than not, we actually expect that misalignment. So we're expanding our model space to try to understand some of these effects. And if we can detect precession, that also relates to lens tearing precession. It's a GR effect. And finally, I'm going to end with what I think one of the coolest things is, if we actually go to space, we can do some amazing tests of fundamental theory. And so here we come back to the beginning of the talk with this Fourier transform, but these are very low ringing and all from the sort of n equals 0, n equals 1. What happens is if you start to move to baselines that can only be probed if we use stations in low Earth orbit, mid, geosynchronous, put stations on the moon, Lagrange points, then we can start to see this ringing of the sharp orders that I talked about at the beginning of my talk. And the way that these amplitudes drop off is the direct prediction of the shape of space-time. So I think these are really exciting things, obviously quite a ways off. And in the near term, okay, I'm going to skip this, but we'll start to see more black holes. But I wanted to mention that in the Netherlands, we're trying really hard to get funding actually to move a station from a sort of mothballed array to Namibia, because it fills a really nice piece of our space we didn't have before. So all the things that are covered in orange show you baselines to Namibia. The more baselines you have, the better your sampling is of the sky. So this can really help us basically make better quality images, help us isolate the shape of this ring better. And we're really hoping to work this out. So I think it's an exciting time also to get Africa involved directly more with the EHT. And there's a ton of stuff coming up that I wasn't going to go through in detail, but I just leave there for you to think about. We have other AGN, we have 2018 data. We had a lot of cancellations because of Corona, especially. Hopefully we'll be observing in a couple months, but we'll see what happens, and more telescopes to come. So I'm going to leave it with this, and I hope I didn't go too far over time, but I'll stop sharing. Let me know if you have any questions.
Yeah, thank you very much, Sarah, for a really exciting talk. And Yingxue, can I ask you to please moderate the question session?
Okay, thank you. Thank you, Francesco. Thank you, Sarah, for the interesting talk. And so here we have a number of questions. The first one is, the EHT results do not rule out the other theories besides GR. Also, there was a paper recently which shows that results do not rule out naked singularities. Can you comment on this? When will we be able to say that it is GR?
Well, I think the answer is really comes down to what I was saying, is that we have these errors, right, where we cannot rule something out at the moment, but we seem to be consistent with GR. And in order to rule out GR, we need to be able to really isolate this feature that I was talking about. Now, there are quite a few people also in the collaboration who are working on things like black hole mimickers, alternate theories, naked singularities, effectively the same tools that we're using right now for parametric and a normal black hole, you can already use to make predictions of what these things would look like. And several groups have been doing this. We actually can rule out a boson star for the EHT 2017 results. It just doesn't fit the distribution. So there are some limits we can make. And I would also like to point out that, at least from the theoretical point of view, you know, some of these theories sort of live in a world apart from the astrophysics, but we cannot ignore the astrophysical constraints. So for instance, if you have something like a boson star or some other weird, you know, item that, or some strange space-time, you still need to explain these huge astrophysical jets. And if your model doesn't couple to magnetic fields, you know, I'm turning it around a little bit, but I think that I think the astrophysics has a lot to say about these models as well. And we need, the problem is a lot of the models don't have very specific predictions yet, either for the exact shape in the metric or the, like for instance, with axions, the exact couplings that you might have with the electromagnetic fields. These are things to be explored in the coming years. So I can't exactly say when this will happen. Probably, we're probably going to need to really go to the space arrays to get to that level of precision. But I think you'll start to see more, you know, more results that are pushing on these limits in the coming years.
Yeah, okay, thank you for the answer. And the second question is also my interest as well. So thanks for such an exceptional talk. A quick question, was that D equals to 6 times square root 3 times alpha times 1 plus delta expression generalized? How was that generalized? And could you please tell us a bit more about variability of the thickness A mentioned in the final slides? So I think these are separate questions. Yeah. Hello?
Sorry, hit the wrong, yeah, I didn't unmute. So that expression is basically coming from the predictions of GR. The generalization in terms of how the exact number comes out has been worked out in quite a few papers. I put those references in those slides so you can look them up. But basically it just comes from calculating the geodesics of light and then the expansion that you would expect. And the 4%, I mean, one of the best papers maybe to look at there would be Johansson and Saltis 2010 that shows you where that comes from. But there's quite a lot in simulations that you could see, some nice movies on the internet that show you where that comes from. In terms of the variability, I'm not sure, I could share my screen again and let's see. So I can go through this a teeny bit more and I'll just say a couple things about this. So so like I said, we have this flickering around the black hole. What's interesting is that when we look over time in the X-ray, these flares can sometimes be broken apart into double peaked flares. And they often will have, so they're on the time scale of what you would expect to have plasma that's moving basically around really at about 5 to 10 gravitational radii. So these seem to be distinct features. That's why we like the plasmoid model, but we're not 100% sure about this at this point, that are moving around the black hole. And some of this double peaked emission might be because of distortion, because if you do general relativistic ray tracing, if you have the black hole and you have a sort of flare of material, a bright blob moving behind it, what'll happen is the light bending effects can give you, it'll be bright, then it can be sort of distorted and then bright again on the other side. That's one of the really interesting things that we might be able to probe with this. And so we're trying to observe together with gravity, because in the infrared, we see these similar double peaked blobs. So we know that these blobs, we have their spectra in several wavelengths right now. And this is actually the reconstructed orbit of one of these flares. So this is the expected shadow size of Sagittarius A star. And these are actual, you know, we don't know if this is a blob moving in the accretion flow. It could be spiraling up a jet that's pointed more towards us. We don't have the information about the projection, but we're hoping to observe together with EHT in this coming year as well, because if we can have all this information together, this gives us quite a lot of information about it. And with these fake, you know, data that I was showing, let me just show one quick. With the same types of things I was talking about with the simulations, we pick a certain prescription to fit the EHT image. And this is now for Sagittarius A star, but we have lots of information about it. This would be where the EHT flux would be. We have information in the infrared. We have information in the X-ray, sort of the quiescent emission, average flares and high flares. And then we can actually start to compare it directly to the predictions of our models with these different particle prescriptions. So I don't know if that addressed the question that you had in particular, or do you want to give a second part?
So Anna, well, I guess that's already quite a detailed explanatory. Okay. Thank you. Yeah, that's perfect. Just maybe there's no more on the Q&A yet. So just
there's an anonymous attendee said, what does putting hair in a black hole mean in terms of Hawking radiation?
Okay.
Well, so the truth is, Hawking radiation is so low signal. I mean, you're talking about, you know, photons coming out as a quantum process. It's really incomparable to astrophysical light. So we cannot detect Hawking radiation. We probably will never be able to directly detect Hawking radiation. It's a theoretical concept. You could study it, but we can't say anything about it, unfortunately, with astrophysical observations, because they're orders and orders of magnitude brighter, and we just swamp it out.
Yeah, okay. There is another question from the chat window. I have a quick question that's quite a bit tangential. But as you likely know, catching a pulsar around Cygnus A is another holy grail for testing GR in a strong field regime. From the astrophysics you are describing, what do you think is the likelihood of finding a pulsar close in?
Oh, so right. There is actually a working group in EHT that's focused. It's being led by Michael Kramer and company to try to find a pulsar that is in the basically gravitational field of Sagittarius A star, because then of course you could test, you know, all the fun things you could do with the triple system you could do in the strong field. It's an excellent question. I am not the best person to say what the probability is. I mean, we have found a magnetar already that's actually in the accretion flow of Sagittarius star. So it's on the order of 1,000 or so. Yeah, is that right? About 2,000 gravitational radii, I think, away from the black hole, but it's not close enough to be affected by the strong gravity. There's a lot of theories that there should be quite a few pulsars around. There's searches going on for this. This is a whole working group, but yeah, I don't really know myself exactly the numbers about the likelihood. I'm sorry. There's definitely some work on this and some papers though coming out. So I think you'll hear some more about this soon.
Okay. Okay, thanks so much. Yes. Okay, if there's no questions anymore, then I think we finish up with the Q&A section.